Hey, so we need to discuss one more notation of derivative. It's the Leibniz notation. Okay, so if you haven't heard, Leibniz was another mathematician working on calculus, the concept of calculus alongside the same time Newton was working on calculus, right? So because they were in two separate countries, they were using two different notations. But Leibniz notation actually has a lot of advantages. Okay, so very simply, okay, if I have y equals, let's say, x squared, we denote instead of y prime, okay, instead of that we write dy over dx, and this is really a shorthand for changing y over changing x, right? This converts into this as x, the delta x gets really small, right? So remember, derivative was equivalent to instantaneous rate of change on a function at a particular x value, okay? So it's more similar to that notation. So this actually better describes what derivative is. Like this prime, where did that come from? It's very nice to write because it's so easy, you just have to put a tick mark on it, but it's not descriptive. So, right, you can write dy over dx as 2x. Okay, dy over dx as 2x. Now, how do we do this with composite function? That's the question. Okay. So here, let's do an example here. Let's say we have a square root of x squared plus 1. Okay, this is clearly a composite function. Okay, here's what we do. The first part, the g, right? So we typically write this as f o g at x. So the g part, we let it be u. So let u be x squared plus 1. Okay. And what we do is the following. If you do that, you get y equals to simply square root of u. And what we do is to get dy over dx, what we do is we first differentiate dy, this function, with respect to u. So how is y changing as u is changing? Times by, now take this function into consideration, du over dx. Look, symbolically, it looks like those two will actually cancel each other out and you get dy over dx. In reality, the argument is not that simple, and I'm going to create a separate video for how to prove the chain rule. And it's a much more advanced topic than an introductory calculus course. So it's optional for you to fully understand that proof. But for now, you can kind of think of it as, right, dy over dx in Leibniz notation is the following. So you're basically multiplying this and this. This is equivalent to f prime g at x times by g prime at x. It's the same thing as that, this portion right here. Okay, so let's apply this notation here, dy over dx. So if you differentiate square root of u, you get 1 over 2 square root of u. Okay, and then you multiply that by du over dx, and du over dx from here, right, du over dx is just simply 2x. So you multiply this by 2x. Let's clean this up. That simplifies. You get x over square root of u, but if you want it as a function of strictly x, which is what we are already comfortable with, all you have to do is get u right here, replace that u with x squared plus 1. And we're done, okay? All right, I kind of took it slow, and me explaining everything in super detail might have confused what's happening here. So let's do one a little bit faster, okay? Okay, so let's try this one. Okay, hopefully you can see that g at x should be that. So you let u equal to 1 minus 4x squared. And this can be written as y equals u to the power of 50. Okay, so chain rule with Leibniz notation is dy over dx then is equal to dy, first of all, with respect to du, and then you do du over dx. So if you differentiate this, we just get 50u to the power of 49. And if we differentiate this, we get minus 4 times by 2x. And to finish it off, let's just multiply everything in here. That's 8. So that's minus 400x. And replace the u back with the x. Okay, and we're done. So that's Leibniz notation with chain rule. Okay, that's it for this one. I'll see you in the next.